Hello everybody, this is Homer White, back again with the second part of the 9th chapter of our course. We're working on confidence intervals. In this part, we're going to look under the hood a little bit at how confidence intervals for one population mean actually do their work. Always remember to make sure that the necessary packages are loaded. First of all, let's introduce the idea of a t-statistic. Think about the 68-95 rule for estimation. The 95 part of it says that we're about 95% confident that the real population mean mu lies somewhere in between the sample mean x bar minus 2 standard errors of x bar and the sample mean plus 2 standard errors of x bar. Why are we 95% confident that that is so? It's because before the sample was taken, we knew that there was about a 95% chance that mu would lie between these two numbers. Let's apply some logic to this situation. To say that mu lies between x bar minus 2 standard errors and x bar plus 2 standard errors is the same as saying that mu is within 2 standard errors of x bar. But that in turn means the same thing as x bar is within 2 standard errors of mu. After all, if I am within 10 feet of you, you are within 10 feet of me. Continue the logic. If you look at the number x bar minus mu, that says how far x bar is from mu. But if you divide that number by the standard error of x bar, then that whole quantity says how many standard errors x bar is above or below mu. Therefore, saying that x bar is within 2 standard errors of mu is saying that this number in the middle is somewhere between minus 2 and 2. We should pay more attention to this number in the middle. Let's define the t-statistic as that number in the middle. We call it t for short, and it's defined as x bar minus mu divided by the standard error of x bar. The t-statistic is the t in t-test GC. We'll learn about test in chapter 10. As we've seen, t says how many standard errors x bar is above or below the population mean mu. Standard errors kind of work like standard deviations did back in chapter 2. They talk about a spread. In fact, the formula for the t-statistic should remind you a great deal of z-scores back in chapter 2. So we say that t has z-score style. Concluding the logic. All along, when we were saying that there was about a 95% chance that mu was within 2 standard errors of x bar, that was really equivalent to saying that this new number t has about a 95% chance of being between minus 2 and 2. Now this is just an approximation. It's based on the 68-95 rule for probability, and then, going on a limb a bit, the 68-95 rule for estimation. But how good is this approximation? And can we do any better? Well, thinking about t a little bit more, looking at its formula, we see that it depends on x bar, and since it also depends on the standard error for x bar, which depends on the sample standard deviation, we see that t depends upon x bar and s. But those are numbers you compute from the sample. And the sample depends on chance if we really are taking a random sample from the population. Therefore, t is a number that depends on chance. By definition, that makes t a random variable. Random variables have probability distributions. What can we say about the probability distribution of the t-statistic? This brings us to the notion of t-curves. Statistical theory has a lot to say about t-statistics. Here's one thing we know for sure. If you take a random sample from a population And if that population is also perfectly normal, so that a histogram of it, for example, would follow the normal curve very, very closely. And if your sample is of, let us say, size n, then probabilities for t are given exactly by a t-density curve with n minus 1 degrees of freedom. What are these t-density curves? What is degrees of freedom? Let's take a look. Well, there's a t-curve for each degree of freedom. 1, 2, 3, 4, all the whole numbers. We abbreviate degrees of freedom, df, for short. T-curves are symmetric, and they're also centered around 0. Now, the standard normal curve is also symmetric and centered around 0. But t-curves are not the same as the standard normal curve. They have fatter tails than the standard normal curve does. However, the bigger the degree of freedom is, the more the t-curve of that degree of freedom will resemble the standard normal curve. You can see this with a little Manipulate app. Let's give it a try. When you run the app, you see in the plot window a picture of the density curve for a t-curve with 1 degree of freedom. As you can see, it's centered at 0. But it's not the same as the standard normal curve. You can see this by pressing the wheel and asking to show the standard normal curve. You can see that the tails of the t-curve are higher and fatter than the tails of the normal curve. There's more area out to the sides for the t-curve and less area in the middle as compared to the standard normal curve. But let's look now at a t-curve with 2 degrees of freedom, or 3 degrees of freedom, or how about 10 degrees of freedom, or 30 degrees of freedom. At 30 degrees of freedom, my eye can barely tell the difference between the two curves. And at 100 degrees of freedom, I can't see any difference at all. Since we know exact formulas for t-curves at any degree of freedom, we can encode these formulas into our functions so that we can find probabilities for random variables that have t-curves as their probability distributions. If a random variable has a t-curve as its probability distribution, we call it a t-random variable. We can use the R function ptgc to find probabilities for these t-random variables. Let's take an example. Suppose that you're going to take a simple random sample of size 40 from a population. Let's suppose further that the population is exactly normal. Then we know that the t-statistic t is going to have exactly a t distribution with n minus 1 degrees of freedom. That's 39 degrees of freedom. Now say we wanted to find the probability that the t-statistic will come out between minus 2 and 2. By the 68-95 rule, we know that probability is about 95%, but that's kind of rough, and we'd like to find it exactly. Well, we can use ptgc just the same way as we use pnormgc. We put the two boundary numbers in as a list, specify the region as between. We have to identify the t-curve, and we do that by giving its degrees of freedom. That's 1 less than the sample size, so degrees of freedom is set to 39. And let's take a look at the graph, too. If you were to take the time to run this in the console, and you probably should pause the video and do that, then you'll see what's on the following slide. Well, the area underneath the t-curve with 39 degrees of freedom, from minus 2 to 2, is about 0.9475. That's almost 95%. So those rough 95% confidence intervals that we would make with the 68-95 rule for estimation actually aren't so bad. They're going to have about a 95% level of confidence. This happens, though, at size 40. What if we tried it with a smaller sample size? So say that you were going to take a simple random sample of size n equals 4 from a population. And again, we'll suppose the population is exactly normal. what would be the probability that the t-statistic would come out between -2 and 2? This time, the only change we have to make in the code is to set the degrees of freedom one less than the sample size, so now it's down to 3. And if we were to run that code, here's what we get. The area underneath the t-curve with 3 degrees of freedom is only about 86%. Remember, the 68-95 rule for estimation was assuming that the chance of the t-statistic coming between -2 and 2 is about 95%. At sample size 4, it's pretty far off. 95% confidence intervals that you make with the 68-95 rule for estimation at sample size 4 won't have the advertised level of confidence. They're really going to be more like 86% confidence intervals. So when we make confidence intervals, we really need to do a better job than just the 68-95 rule for estimation. This brings us to the topic of multipliers. Think back once again on our rough 95% confidence intervals from the 68-95 rule for estimation. Such an interval is constructed by taking the sample mean and adding and subtracting 2 standard errors for the sample mean. In general, whatever we're using to estimate a parameter, if we're using the 68-95 rule for estimation, we take that estimator, whether it be an x-bar or a p-hat or anything else, and add or subtract 2 standard errors. The number 2 here is a multiplier. It makes the interval into a rough 95% confidence interval. Other multipliers would give you other levels of confidence. For example, when you use 1 as a multiplier, you end up making a rough 68% confidence interval. That's x bar plus or minus 1 standard error of x. And in the 68-95 rule for estimation, if you would use 3 as a multiplier, you would end up with a rough 99.7% confidence interval. X bar plus or minus 3 standard errors for x. Well, t-test GC in R is also going to use multipliers to make its confidence intervals. However, they're going to be more careful about it. They're going to work things so that if the population is exactly normal, then those confidence intervals yield exactly the level of confidence that they advertise that they have. How does R find these better multipliers? Well, let's work from an example. Say that you've taken a random sample of size 16 from a population, and you know the population is normally distributed, but you don't know the population mean mu or the population standard deviation sigma. So maybe you want to use your sample to make a 95% confidence interval for mu. You know that your interval needs to look like the sample mean x bar plus or minus some multiplier, which we will call t star, times the standard error for x bar. So t star is going to be the multiplier for a 95% confidence interval for mu at sample size 16. At other sample sizes, there will be a different multiplier. At other levels of confidence, there will be a different multiplier. Now let's think this through. What we want is a number t star so that the probability that the t-statistic t comes between minus t star and t star is exactly 95%. Remember, 2 as a multiplier does not do the job. It never does it perfectly, and it doesn't do it very well at small sample sizes. What's the right number at sample size 16? Well, we need to find that number so that the area underneath a t-curve with 15 degrees of freedom, one less than the sample size, is exactly 0.95. We can look around for numbers so that the area from minus that number to plus that same number is exactly a 0.95. And if you look around enough for yourself, you'll actually see, eventually, that if you choose the number 2.13145, the area underneath the t-curve from minus that number to plus that number is just about 0.95. So it looks like 2.13145 should be our choice for the multiplier, t star. Now, R doesn't find that multiplier by just bumbling around and trying out a lot of different choices. It has a quick way of finding it. But find it does. So at sample size 16, R computes a 95% confidence interval using the formula that you see right here, x bar plus or minus the chosen t-star multiplier times the standard error for x bar. Remember, that multiplier depends on the sample size n, and it depends on the desired level of confidence. In the output of t-test GC, R doesn't mention the multiplier explicitly, but you see its effect in the computation of the confidence interval that it does report to you. Just a reminder here, if the population is not exactly normal, then R's formula for confidence intervals won't be exactly correct. But even if the population is not normal, as the sample size n increases, the formula for confidence intervals that R uses does get closer and closer to correct, in the sense that the advertised level of confidence gets closer and closer to the actual level of confidence. All of this can help us to understand why safety checks are fairly important. It's all about truth in advertising. Suppose that you want to make intervals at a certain level of confidence, say 95%. For your method to be a reliable one, your intervals should contain the population mu 95% of the time in repeated sampling. Now, our statistical theory says that if the population is normal, and if you took a random sample from the population, then this will happen, and it will happen at any sample size. But if the population is not normal, then the intervals are only approximately 95% confidence intervals. Now, at very large sample sizes, this is not a problem. This has to do with the central limit theorem that we learned about in Chapter 8. But at smaller sample sizes, you really have to have some good reason to believe that the population is not too far from normal if you want to be able to use these confidence intervals as approximately 95% confidence intervals. You can see this for yourself. You can examine the effect of non-normal and highly non-normal populations on the actual level of confidence for confidence intervals generated by R. We have an app for you. It's a shiny app called CI-mean. Now, there are various ways to try to run this app. If you happen to have a desktop version of R, then you can run the first set of commands. You do have to install from CRAN the package Shiny first. It's also possible to get this app from the web directly without using R at all, although at the moment all these methods are in alpha testing stages or are somewhat shaky. But you might try either of the following websites. So you could pause it here and decide how you're going to find this app, or you could just follow along and I'll play with it a bit and show you what's in it. When you open up the app, it shows you a density curve for a perfectly normal population whose mean is 70, indicated here by the vertical line. We're going to be able to take samples from this population, and you can choose the sample size using a slider over here. Let's keep it at sample size 2. Once you take your sample, you can make a confidence interval for any desired level of confidence. Why don't we keep it at 95% confidence right now? You can also take just one sample at a time or a whole lot of samples at once. We'll just take one sample right now by pushing this action button. It was a sample of size 2. The light blue there is an attempt at a histogram for this sample, and so it's a pretty ugly histogram given the small sample size. The sample mean for those 2 items that were picked is shown by the blue dot here. It's a little larger than the population mean, but if you construct the 95% confidence interval based on this sample, that's in yellow here, you see that it extends quite widely, and in fact it does contain the population mean. Let's try it again. We're probably going to get a lot of wide intervals, and that's because the sample size is so small. So far, all but one of our intervals has actually contained the mean. One of them turned out to be quite narrow and did not. If we would really like to tell whether the intervals contain the mean 95% of the time in repeated sampling, we should probably take a lot of samples and just summarize the results. Here, let's get 5,000 samples at once. Let's take the samples. Out of our 5,000 samples, we see that 4,770 of them did contain the mean. That's 95.4% of them. If we could have done this millions of times instead of just 5,000 times, then we would have found that even closer to 95% of those samples contained the mean. That's because the population is perfectly normal, and all of the theory that underlies our confidence intervals is perfectly satisfied. If you're interested in looking at the confidence intervals themselves, here they are. Well, this is the first 5 of them, and as you can see, the first 5 all contain the mean. If you want to see more in the list, you can push the next button and you'll see more intervals. But there's 5,000 of them, no use looking at them all. Let's try a bit larger sample size. How about sample size 10? Take the samples. Still about 95%. Statistical theory says that if the population is perfectly normal, then no matter what the sample size is, the 95% intervals will contain the population mean about 95% of the time. That seems to be working out. One way to see how this is so is to look at the t-statistic tab. What we see here is a picture in red of the t-curve with 9 degrees of freedom, because we were at sample size 10. And in blue, we see a density curve that shows the distribution of the 5,000 t-statistics that come from each of the 5,000 samples that we took. As you can see, there's hardly any difference between these two curves. After all, statistical theory says that the exact distribution of the t-statistic is a t-curve when the underlying population is normal. But what if it's not normal? Set the sample size back to 2. Take one sample and look at maybe a skewy population. Here's the population in red. Its density curve has a big tail off to the right. As you can see, the mean is 100. Let's try taking 5,000 samples from this rather skewy population. It wasn't so bad. Look at that. These 5,000 confidence intervals contained the mean of 94% of the time, not far off the advertised 95%. Was this a fluke? Let's try another 5,000 samples. 93%, 93.5%, 93.5%. Oh, a percent or a percent and a half below. But that's not far off. Let's try a little bit bigger sample size. How about sample size 5? My goodness. Now we only contain the mean 91% of the time. About 91.5% of the time. The level of confidence actually went down, even though the sample size went up. Try sample size 12. Back up to 93%. How about sample size 30? %, 94%. Seems to be about 93.5% of the time. Sample size 50. Whoa. back up to the 94% or so, pretty close to the advertised 95%. So if you happen to be just taking one sample at a time, and you take a histogram of your sample and you see that it's rather skewy, if it's skewy but not too skewy, and the sample size is fairly big, then you know that you can trust the confidence intervals to have approximately the advertised level of confidence. Let's go back to sample size 2 and try a really skewy population. This one has a very, very long tail. And we'll try 5,000 samples from it. These advertised 95% confidence intervals at sample size 2 from the super skewy population really only have a confidence level of about 89%. Let's pull the sample size up to maybe sample size 10. I assume things will get better. They don't. 85%? 86%? Things actually got worse. Pull the sample size up again. Say to 20. Yeah, getting better. 89%. Sample size 30. Yeah, not much better. Still around 89%. Sample size 50. Only about 91.5%. This population is so skewed that even at a rather large sample size of 50, these confidence intervals have an actual level of confidence that departs rather substantially from their advertised level of 95%. Let's go back to taking one sample. If you take one sample from a population like this, and you see a very big long tail, then you know not to trust these confidence intervals that you would make from that sample, even if the sample size is pretty large. So maybe it's always a good idea to look at your sample, even when the sample size is large. By the way, let's take a look at the distribution of the t-statistic at this sample size from this very skewy population. Let's take 5,000 samples, look at the t-statistic. The distribution of the t-statistic based on the 5,000 samples is in blue, and is being compared with a t-curve of 49 degrees of freedom. As you can see, there's some left skewness to this t-statistic. It's fairly substantial. That contributes to the confidence intervals not having the level of confidence that they advertise. Let's go back to sample size 2. And let's try, one sample at a time, a way out outlier group population. This population is such that about 90% of the values in the population are somewhere around 50, and about 10% of the values are around 200. The actual mean is here at this vertical line. Now, what would happen if we were to take 5,000 samples from this population and see how often the confidence intervals cover the mean? Well, these 95% confidence intervals covered the mean only about 77% of the time. Was that a fluke? Let's try again. No, it's around 77%. Well, things will probably get better if you go to a higher sample size. Let's go to sample size 10. Oh my goodness, things actually got worse. These purported 95% confidence intervals are actually more like 65% confidence intervals. Let's try all the way up to sample size 50. Even there, things aren't looking very good. The advertised 95% confidence intervals are really only about 90% confidence intervals. Why is this so? Let's take a look at the distributions of the t-statistic. First, we'll set the sample size low. We'll take our 5,000 samples, and we'll look over at the t-statistic. My goodness, it's very spiky, and a big funny tail to the left. As compared to the t-curve with 1 degree of freedom, it's almost a completely different thing. Let's try a little bit bigger sample size, maybe sample size 10. Pay no attention to the curve you see there. The browser is just having kind of a nightmare. We'll take the samples. It's very spiky still. There's more bumps. At sample size 24, there's still more bumps, and they're closer together. The t-statistic distribution is starting to follow the t-curve a little bit better, but it's still kind of wacky. Sample size 50. Still very wacky. Statistical theory says that as the sample size gets bigger and bigger, the distribution of the t-statistic will get closer and closer to the relevant t-curve with the n-1 degrees of freedom. But as you can see, for some populations, it takes quite a long time for the t-statistic to look like the t-curve. Going back to just one sample for this very crazy population. If you were to take a sample like this and make a histogram and you saw that most of the values were in one place, but there were also some values way off in another place, then you would probably suspect that this population has two very distinct subgroups. And you might not be that interested in making confidence intervals for the mean of the population anymore. You might want to know more about the means of each of the subgroups. As you can see, looking at a graph of your sample can be very important in deciding whether to trust your confidence intervals for a mean. They can also be very important in deciding whether the mean is all of that interesting thing to want to know about your population. So let's review. The basic safety check for one mean is that at smaller sample sizes, say n less than 30, definitely make a histogram or a box plot of the sample. But it might be a good idea to just go ahead and make a histogram box plot all the time, just in case your population is one of the pathological ones that we've looked at. Now, at those smaller sample sizes, if you see much skewness, you need to be worried. If you see outliers, be worried. The smaller the sample size, the more the skewness or the outliers that you see should worry you. At very large sample sizes, the statistical theory says that the skewness and the outliers won't make much of a difference. But much more important is the other part of the safety check. We need to have taken a random sample from the population for any of this statistical theory to have any chance to apply. If our sample was not random, if it was one of those samples that's subject to sampling bias of the sort that we saw in Chapter 5, then no amount of clever probability theory is going to help us make reliable confidence intervals. Just making a confidence interval doesn't do a thing at all to correct for a biased sampling method. Thank you for listening.